Okay, good evening, everyone. So I'm very happy to give a talk about our recent, maybe just 10 years past for our research on phonons and the emergent novel effects. Uh, yeah, uh, okay. Yeah, this outline, this in my talk will include topologic phonon, and because this work may be about topologic the phonon, I was done this maybe 15 years ago. Yeah, because I'm very interested in the phase of phonons, then studied the topological phase of phonon, and then just maybe do some work on the phono Hall effect and find some topological effect of phono. After that, I moved to UT Austin and do postdoc and continue doing the research on the phonons and find the phono angular momentum that also is in the some magnetic systems. We found that the phonon can have angular momentum. And after that, for the usual, for the non-magnetic system, so how about the phonons? Maybe the total angular momentum will not be zero. So how about each mode? So we found that each phonon mode can also have angular momentum, but maybe the total the angular momentum will be zero. But for each mode, they have angular momentum, and they can have some effect in the maybe the intervalley scattering of electrons when they absorb the phonon or emit phonons, then maybe need to have some selection rules for the kind of phonons. So after that, they maybe a lot of works have maybe followed the phonons. You especially this years, every year maybe have the 100 to 200 papers on phonons. So I'm very happy to see such a hot field for the phonon. And but because the phonon can we will put in attention to the wave function for the phonons, then can give us more uh, freedom for phonon manipulation or some application for phonons. So yeah, so today I will introduce our the work on for this topology and phonon angular moment and phonons and recent works. Okay. Okay, because phonon, maybe I don't need to tell much about phonons. Phonon is very important quantum particles. It's especially in kinetic matter. Now, not only in kinetic matter, the phonon is very widely in various physical phenomena, such as heat conduction and thermoelectric effect and photothermal effect, electrophonon interaction in the kinetic matter, and the superconducting Cooper pair. And the Raman scattering. All this may be related to phonons. So if we have get a new physics for phonons, then maybe we can do all the research for the related phonons to give us a new picture. Yeah, we understand the phonon and the related phenomena. Okay, the phonon, in the kinetic matter physics, the textbook, we know that a quantum collection, excitation, and lattice vibrations, the typical boson quasi-particles, and and have a quantum number for phonons, and the phonon distribution will have boson distribution. Yeah, and typically this is graphing the phono dispersion relation. Yeah, maybe we most of us know that. Yeah, but in all this with phono dispersion, we care about the phonon energy and from the k wave vector and the group velocity and maybe some scattering rates for phonons. So all this maybe we only pay attention to this physics property for phonons, and almost we never care about the phonon wave functions. Yeah, but for the electron case also, because before 20, maybe 40 years ago, we only care about the electron energy and electron maybe the spectrum, and we also never care about the electron wave functions. But only after the very first effect, we know that maybe the wave function for electrons is very important for the condensed matter. So after that, especially recent decades, okay, maybe the topological physics, topological matter can insert the insulate, topological insulate is a very hot field. So in condensed matter physics. So we are just because inspired by the electron case, so we also are interested in the wave function for phonons. So how about the phase effect for the phonon wave functions? Yeah. So that after we do care about the phonon topological nature of phonon Hall effect. Yeah, the phonon Hall effect is just 20 years ago, we found in the parametric magnetic systems, if we apply a temperature difference in the longitudinal directions of a temperature difference, then apply magnetic field perpendicular to this plane, then we can find the temperature difference in the transverse direction. Yeah, but because the phonon cannot couple to magnetic field, so how about this effect can happen? So we just from a microscopic picture, maybe each atoms will have a called effective charge. On the magnetic field, then we'll have a Lorentz force. So it just in this simple picture, then we can get this kinetic energy in this form, and also we can write a Hamiltonian like in this form. So here we will have another terms for the phonon. This is quite different from the harmonic case. Yeah, harmonic, the phonons for the harmonic case only have this term, and then know this such terms. So here, this just we can understand this like each atoms have magnetizations. So this magnetization, when this do some optical, some vibrations, this will have like some spin optical interaction. Yeah, this spin, maybe spin for the atoms, and magnetization for the atoms, then we are coupled to the optical vibrations. This is spin of the interaction similar. So in this picture, then we have such kind of Hamiltonian. Then how about the wave picture for the phonons? Yeah, for this Hamiltonian, and this we can understand this Hamiltonian from other picture, like maybe you have different source for this Hamiltonians. We understand from the effective charge have Lorentz force, but still we can get this term from other picture, like quantum mechanisms. We can to analyze this system by symmetry. Then we also can get such kind of terms for the phonon and the magnetization. And also we can get this term from another picture, because when the the relation not is violated. Yeah, then the electron of the atoms will get the effect by the vibration of the atoms. Then from that kind of term also can get such kind of spin phonon interaction terms. Okay, so get such kind of Hamiltonian. How can we solve this Hamiltonian? Yeah, then we can solve from the momentum, the vibration, that maybe this is coordinate, this is the momentum. Then we can get this Hamiltonian. It's non-Hermitian. Yeah, non-Hermitian. So how can get such kind of non-Hermitian term? We need to get the left angle function and the right angle function. So from the angle right, left or right angle function, we can get, yeah, can get some get calculated the heat flux and the Berry curvature, yeah, from this sorry, connection and Berry curvature. Maybe I forgot another slides. Yeah, from that slides we can get the conductivity. Yeah, Hall conductivity. So yeah, so from this maybe just a start of the topological nature for phonon Hall effect. Yeah, from here, this non-Hermitian system. This is the standard non-Hermitian system. We get the left angle function and right angle function. Then we can calculate the Berry connection and the Berry phase. And maybe forgot maybe another slide. Oh, okay, sorry. So from here, we can calculate the Berry phase and the Berry curvature. And from Berry curvature, we can get the whole conductivity. We found the topological phase transition for the phonon Hall effect. So this just do some the topological nature for phonon Hall effect. Okay. Okay, so for after topological nature for phonon, then we can generalize this system to the magnons. We also get to this topological magnon incidents. Yeah, only very recently for the phonon and the topological magnon becomes hot because many people have transferred from topological nature for electron move to phonon and magnons. So my paper, yeah, is top cited after 8 years, but just in when 8 years ago, no guys care about this, but after 8 years, this paper becomes hot cited, yeah, top cited. It's quite interesting. Okay, so after this topological nature for phonon for magnon, so how can we get some very good and various phonon thermal Hall effect for various? Yeah, this we came from the semi-classical picture. We get maybe we can define the maybe the particle magnetization and the energy magnetization. So this is the standard derivation for the electron cases. Yeah, semi-classical theory, how the electron Hall effect. So we just generalize to the thermal Hall effect. We define particle and energy and heat. Then we can get the from all the thermal Hall effect in this picture. Yeah. So this is this Hall conductivity we can generalize to the electron thermal Hall effect, phonon thermal Hall effect, and magnon thermal Hall effect. All this can be included in this formula. Okay, so this after this maybe now we do some for the non-linear phonon Hall effect for the non-magnetic system. Also can find some phonon Hall conductivity. Okay, so this is why I talk about the topological phonon, because we do the phonon study in the magnetic systems. So therefore, the magnetic system, we we have some another effect is Einstein-de-Haas effect. When the apply a magnetic field or turn on the electric field, then this system will have a magnetic field. Then we can find some rotation for the cylinder. Okay, so here is to measure the maybe in the system how the magnetic the ratio for the magnetization and the angular momentum. Okay, so in this system, Einstein and the Haas they consider the angular momentum only for the total, the cylinder, so the lattice, and the angular momentum's spin, and the angular momentum have the orbital angular momentum so for the electrons. So how about the phonons? Whether this system, magnetic system, for the phonon also have angular momentum or not? Yeah. So here then we derive the angular momentum for each atoms. Yeah, here already do mass normalized. Here is R times P. Yeah, P have mass. We just ignore this. Maybe we can do mass normalized. It doesn't matter. Yeah. So angular momentum for this term is for the lattice, the total lattice. Maybe strictly we could call this for the cylinder. Okay, for the rigid body angular momentum. So for the phonon cases is this term and times this term. Okay? So how about the angular momentum for phonon case? And so for now, if for equilibrium case, so the cross term, this one times this one and this one times this one, it will be zero because this is one order for u or u dot. Average will be zero. Okay, but here for this term is one order for u, one order for u dot. So how about this result? Yeah, so we derive this, yeah, okay, and get the phonon angular momentum when do the second quantization. Then in equilibrium, we find that the angular momentum will get for phonon will be this. Yeah, each mode will have angular momentum. Okay, and if the temperature is zero, then this will be non-zero. Also, it is similar to the 0 point energy for the phonon. Yeah, here we also have 0 point angular momentum. Yeah, so how about the angular momentum? If this term is zero, so nonsense. Okay, but so how about this? Whether this is zero or not, so we calculate for this. Yeah, this we are rewrite the phonon Hall system here. Yeah, we use the same Hamiltonian to calculate the phonon angular momentum. Okay, so for the harmonic cases, it's zero. Yeah, because the symmetry consideration. This each term, each minus k and the k, they will be odd function. So the total phonon angular momentum will be zero. Okay, for the phonon Hall system, this because time, yes, the times inversion symmetry is broken. Okay, then we just because the spin phonon interaction, then this relation will not will not be odd function. They cannot cancel each other. So the total phonon angular momentum will not zero. Okay, so we calculate for each mode and for where if the temperature is larger than double temperature, because each mode will cancel each other, the total angular momentum will be zero. Okay, only in the temperature lower than double temperature, especially in near to zero, then the angular momentum will be larger. So how to experiment measure this? So we get a proposal. Yeah, if the temperature change, then the angular momentum will be changed. If the temperature is both temperature lower than Curie temperature, then the angular momentum from magnon will not change, but the angular momentum for phonon will change. So we can find this change come from the phonon cases. So just because this maybe just very recently they do the an experiment of verification in some nanosystems. Okay, but we first just after this publication, we do some collaboration with others. They do some macroscopic cylinder to measure, but because the magnet easy to control, so yeah, it's very difficult to make the angular momentum. Just very recently, they do the angular the verification in nanosystems. Okay, okay. So here we get the non-zero phonon angular momentum, but yeah, in the maybe large, yeah, maybe room temperature, this effect is so. How about the non-magnetic system? Okay, but for the angular momentum, the verification is verified by this work. Okay, so this is for the demagnetizing system. Yeah, we yeah, for Eisenhower effect, if we put a magnetic field to the system, then because the angular momentum conservation, they will rotate back, okay? Because the angular momentum conserved. But so for the demagnetization system, also, if we use a laser to demagnetization this system, then we also need to find some rotation for the system, okay? Because when you demagnetizations, the electron, the angular momentum for electron is maybe disappear. So, but they cancel each other. So the cylinder will have some angular momentum will maybe come back or not. But we did never find this is angular momentum. So the from angular momentum is disappeared. So this is a long puzzle for this system. So just very recently, they have energy spectrum maybe to find this, use the electron kit to find, they find that the angular momentum does not disappear. Because each atom, they do the vibration just inside, but then the magnum case, it transfer an angular momentum to the phonons. So each atom will do angular vibration inside. So this just can be a verification for phonon angular momentum. Okay. Okay. So just I may just mention just now, yeah, very recently they do the for the next change the temperature, then can find some angular momentum. Okay, so for the nanosystem, that's a very recent. Okay, okay, so for the magnetic systems, it's can find the total number non-zero for no angular momentum. Yeah, for it's a macroscopic effect. Okay, we have a macroscopic effect for the total for no angular momentum. Okay, for the maybe for the non-magnetic system, how about the phonons? We still can do the research. Okay, because we still to study the symmetry for the angular momentum. Yeah, the angular momentum is odd function for k, okay? For the because this is like because it's r times p, okay? P is dr dt, so it's odd function for times, okay? For time reversal, this angular momentum will change sign, but it was a spell inversion because this have r and dr dt have 2r. When r change, okay? It's a even function for the maybe for the spatial inversion symmetry is a even function. Okay, so if we for the magnetic systems we break the time reversal symmetry, then okay this cannot cancel each other. Then we'll have maybe let's have a macroscopic the total number for the angular momentum. But if we didn't break the time reversal symmetry, then the total angular momentum. But if we break spatial inversion symmetry, okay, so we still can find angular momentum for each mole, but they may cancel each other. But for each mole have the angular momentum. Okay, yeah, because already break one of the symmetry. Okay, so we can find the non-zero for each mole. Yeah, so we just do calculation. Okay, for this honeycomb A/B lattice. Yeah, we just calculate for the wave function for each mode. Yeah, because maybe in the textbook we care about only to long wave limit. Okay, so for long wave limit, it's maybe it's LATA. Is maybe they can vibrate in the same direction or the opposite direction, but mostly they are linear polarized. Okay, because they can only talk about the K point, the gamma point. Okay, but for the K point, we find that they do a circular polarizations. Yeah, each mode can have the angular momentum, have a polarization. Okay, so here it is, yeah, especially for the mode 2 and 3, there is a circular polarization. Okay, yeah, so this circular polarization, when we can uh, to analyze as maybe similar to the photon cases, we can write some two base this this eigenfunction. Then each eigenfunction can write in this form. Two parts. One is for left, one is for right, and this relation. Okay, this relation is exact the same with we derived before. We derive the angular momentum for phonons. Here we have this from the formula. This is exactly the same with this. So this is a very maybe straight picture. Yeah, this the angular momentum. The angular momentum for each mode is come from atoms with each atom when they do some maybe circular or some ellipse relation vibration. Will get this phonon angular momentums. Okay, okay, we can plot this SA as the polar. Maybe we call this S is the polarization for atom A, polarization for atom B, polarization for totally is for phonons. Yeah, if charge, then we can get magnetizations. Okay, so why? So very recently we can study the phonon magnetic moment. Okay, this just the main because if each atoms have effective charge, when they do the circular polarization, they should have magnetizations. Okay, yeah. So this is maybe quite straightforward picture. Okay, so for we just plot the one straight one angle mode for phonons for the this is honeycomb lattice. Yes. Okay, each atom will do the circular polarization. Yeah, so it's quite interesting. Yeah. Okay, so for this some circular polarization, uh, when we do the threefold rotation, then for this we can get the pseudo angular momentum. Okay, singular angular momentum because when we do the threefold rotation, we get a phase change. This phase change we can define some pseudo angular momentum, and the first phase change come from two parts. One is from the spin says the self-rotation of atoms. Another is from the optical part. Optical part because the periodic the cases for the atoms. Okay, we can from because yeah we do some rotation. This atom will come to here, then to here. So this we can get the orbital part for the third angular momentum. Okay, with for the so spin part is the self atom self rotation, and orbital part just because the unit to cell will change because when do the rotation this may come to here just because this unit cell come to this unit cell. Okay, so just this threefold rotation, we can define the phonon pseudo angular momentum. We get this. So this pseudo angular momentum just defines the symmetry for phonons. So we think about in the and in the yeah, electron intervalley scattering. Okay, so for the inner valley, okay, in intravalley scattering, we observe the photons just because energy change, but momentum doesn't change. Okay, but if the electron can come from one valley to another valley, then momentum will change. But the photon cannot have so large momentum. We need phonon involved in this process. Okay, so here, so if we solve the whole systems, we need to consider the conservation for energy, for momentum, and for symmetry. Threefold, threefold rotation symmetry. Okay, just because the threefold rotation symmetry in the inner valley scattering the photon will have a can is selectively, okay, can be left rotation or right rotation, okay, just because of the threefold rotation. Okay, so if we for the intervalley scattering also have such kind of selection rules for phonon, okay, so we get this maybe formula when if we do some we have some intervalley, we need to consider this so the angular momentum for phonons. Okay, and we also can calculate the Berry curvature for the phonons. Then we propose some value for the Hall effect. If we apply some string, okay, so some string gradient, we can push the phonon go along some direction. Okay, we may find some phonon value for the Hall effect. It's similar to the electron very very high effect. Okay, but so far have never been verified. Maybe yeah, in the future can find some. We can maybe push forward one value phonons along some definite directions. Okay, so this and after this proposal, then we collaborate with Han Yuzhu in the Berkeley. They do this experimental detection for the conformers. It's exactly the same with our theoretical proposal. Yeah, it's published in Science. So after this publication, then many guys are interested. Yeah, more and more people interested on the conformers. Yeah, and we also collaborate with some people. And after this, we just publish when because the graphene have no didn't have no symmetry breaker because it's well, how can we get a symmetry breaker? We can put this boron nitride. Yeah, this then can break the symmetry, and we can get the Chiral phonons and can manipulate the Chiral phonons. Yeah. Okay. And for the other some because since for the maybe the calculatis, yeah, because we just I mentioned before, I do some magnum topological magnum. Yeah. For the topological magnum, they mostly studied in the calculating lattice. Yeah. Yeah. Calculating lattice, yeah, have some skamion or some others because the DM interaction. Okay. So here, so we calculate for the phonon cases. How about this system? So you symmetry for the there's inner cell and outer cell. They have maybe the different spring constant. Then we can break the symmetry like this. This will have a threefold. Before this, it's a sixfold rotation symmetry. But now they have threefold rotation symmetry, and we calculate this. The phonons is quite interesting. They have this the elliptically polarized chi phonons like this. Okay, and although this is the elliptically chi phonons, they still have threefold rotation symmetry. They still have a very good pseudo angular. Yeah. So here, so when you do the threefold rotation, they're still the same. Okay, and calculate the Barry curvature uh, and also because for just for the um, previously we do the interval scattering by maybe we need first excite a photon in one valley and another or her scattering to another valley. So when in another valley, the phonon will evolve one step case is just only from one from gamma to k, just because this is maybe indirect band gap, so can have such kind of scattering from k1 one k to another k or one gamma to this k point. So if the electrons scatter from K point to gamma point to the K point from the maybe the valley band to the conduction band. Okay, so here then we need to consider the photon. This is energy change in this first step. Okay, the phonon and photon and the electron, they will combine together. Okay, okay. It's in the experiment can also verified this dark exciton brightened by color phonons. Yeah, in previously because we never consider the phonon also have the pseudo angular momentum. So we find maybe we think that in this case they cannot happen. So cannot find such kind of excitons. But now because this phonon they can have this pseudo angular momentum, they can be evolved in this process. So we can find some dark these excitons can be found in this process. Okay. Okay. So for this for some gamma point, they know they have just basic LOTO. This case is see, yeah. How this is a degeneracy point. So for the degeneration point, we can have longitudinal or transverse mode. But because the energy is the same, we can do the quantum superposition. Superposition. So for this case, we can do after do the quantum superposition with vibration. Another is right to hand vibration. We can do is x plus iy and x minus iy. Okay, if in this case is well can be a circular be a so how can get this kind of point? We just need photon. Okay, inside if photon have is you will in the phonon evolved, then because the photon have one or minus one is the pseudo angular momentum. So when one minus minus one will be zero, but because this the photons can only have pseudo angular momentum is one or minus one. So in this case, the well if one minus minus one will be two, but 2 is the same with minus 1. So for the left-handed photons, we emit a phonon and a photon with minus 1 pseudo angular momentums. Okay, so if we inject linear polarized photons, then because the linear photons is the combination of left and right photons. Okay, so but for the right and the left, they emit different photons. So in this case, one is left, one light, one photon will emit another photon will emit the opposite phonons. So in this case, they will entangle together. So we'll get the entanglement of chiral phonon and photons in these cases. Okay, so for all these phonons, we just care about the phonons mostly in the K point in the boron zone, in the edge of the boron zone. Okay, but in the edge of boron zone, the group velocity for phonons is zero. So if because nowadays we can have maybe new degrees of phonons, they can be left, be right, can be positive or be negative. Can we use this for some maybe conceptual phonon device or not? We need the phonon can transport, can propagate along one direction. Okay. So now, so we just extend this to the three-dimension cases along the symmetry line. We find that that the phonon can have large group velocity. Okay, in this symmetry line, then we can propagate the phonon along this symmetry line. They have a group velocity and have a pseudo angular momentum and phono have a phono angular momentum. So this is maybe some guys later call this a real higher phonons because now this phonon can propagate, have a group angular moment, group momentum, okay, along one z direction, and they also have left or right circular vibrations. So this k times p will be maybe L times P will be -1 or -1. It's helical, okay? So this is a real chi phonon can be propagate along that direction. But here the right chi phonon and the left chi phonos, both of them can transport in one direction. Okay, so can we divide this? Divide this phonon, two phonos, because we only need one correlated phonos propagate along one direction. Can we get this? Yes, we can get this in Kyle materials. So in the Kyle materials, we find for the left or for the right phonos, they have different group of velocity. So here we can find for the right angular moment, right phonos, right-handed phonos, their group velocity is positive. But for the left angular momentum phonos, they have a group velocity is negative. So yeah, so this right can only propagate in this direction, and left the left in another direction. Okay, yeah. Now here can propagate on this direction, but for this cannot, because yeah, because of this is because this materials is chirality changes. So for this chirality changes can have this only left-handed phonon can the chirality and the kind of phonos they're locked together. So for the left right helix materials is right for the left helix materials the left handed phonos is positive. Okay, so they are quite next of the material, then the phonon will change. For one helix material, chiral materials, there the two phonons will have two, and the two correlated phonons will have opposite directions, group velocities. Okay, so here is quite interesting because it's related to some biomolecules. Okay, for biomolecules or the micro crystals for the biomolecules, because sometimes we for the different correlated the materials maybe they have quite different properties. Why this? Okay, because if we uh, some maybe some medicine they why this have different properties. maybe they have when this medicine coupled to human body, they need some interaction. Maybe need the vibration or some coupling. They need also need the maybe phonon will evolve. But for the phonons can only propagate in one direction. Now, so if for another chirality materials, they cannot feel this. Okay, when you feel somebody feel something, need some interaction. This interaction may be the phonons. So it's maybe can give us some new ideas for the life system. Okay, so that because for the life system, for the molecules, all the molecules are left-handed correlatives. Okay, so why this? Maybe and why different chirality molecules they have quite different properties. Okay, uh, okay, and we can get also some study on the chiral manipulation in TMD internet. Okay, yeah, there's just some manipulation. Okay. And the phonons can also activate the spin feedback effect. Just as I mentioned before, because angular momentum is circular polarization, okay? So if you have some effective charge, but most materials atom will have Born effective charge. So from this picture, we know that the vibration will have magnetization in local, okay, in some everywhere. Maybe if you can inject or some emit some phonons, these phonons can affect the electrons, okay, because this vibration and also the atoms have charge, then this will affect the spin polarization for the electron cases. So we can do some calculation and if for the because the temperature difference, if this temperature difference applied, then each atom, the angular momentum for each atom cannot cancel each other. For the equilibrium cases, for this system, for non-magnetic system, the angular momentum will cancel each other. But for the for non-equilibrium system, because the temperature difference, then the angular momentum for each atom when they calculated together, then they will have non-zero effect. They cannot cancel each other. So just because this, so now there's many materials can find some the temperature um, activated the chiral and chiral, then total chiral non-cancel chiral effect, then we'll have that will affect the electron spin polarizations. Okay, so yeah, for the materials, we chiral activate spin feedback effect. That's because the non-cancel effect for chiral angular momentum and the chiral angular momentum because the effective charge, then we'll have some spin polarization effect. Okay, so this may be just a very simple picture, but for we now also do some research on the maybe because the electron and the phonon have some very curvature, very connection. This wave, the phonon wave function will affect the electrons. This will give the electron uh, more maybe your extra the magnetic moment. Okay, so this will give another picture. Yeah, just because of extra magnetization, extra very curvature for the electrons. So we'll get some large magnetic moment. Okay. Okay. And we also do some test trial for the how about the phonons interact with electrons. Yeah, just because we from the electron phonon cases, we can write some electron-phonon interaction in another terms. We maybe most of us may be familiar for the Cooper pair or electron-phonon interaction. They may just for two electrons, one phonons. Okay, when electron uh, to collide with another phonon will be another electron. So will be third order terms. But now when this the chiral phonon come in, just maybe will animate in one direction and emit in another direction. This is chiral phonons. Okay, so this it will maybe disappear in x direction and appear in y direction. Okay, so this will be high phonons. So this is the two phonon cases in the electron phonon coupling. Why this may happen in this electron phonon interaction? Because in the sumo transport, when we consider the phonon coupling, nonlinear phonon coupling, this for nonlinear phonon coupling have three phonon cases. Okay, just maybe two phonon combined to another phonon, or one phonon becomes two phonons. All these are three phonon cases. Okay, three phonon interaction. But most recently, they found the four phonon cases is very important in the scattering process. So in some materials, the four phonon cases will dominate in the scattering process. So why this in the sumo transport cases, we think about the four phonon case interaction. While in the electron phonon interaction, we only consider the three order terms. Okay, just two electron and one phonons. Why they these three two electron and two phonons still can be still can exist in the process. Okay, so this is one cases for these three four order cases. And for this electron phonon coupling, we can have this new kind Cooper pair. Maybe we call this also Cooper pair, or maybe it's cannot call this Cooper pair, but it's a pair. Okay. So for this pair, yeah, then we also we can maybe for this we calculate this pair and how this affect the temperature, superconducting transfer transition temperature. We find we can increase okay the temperature okay about the maybe the uh, yeah so just try okay sorry yeah okay so here we just collaborate with other people in our department they do some superconductivity calculation so we just get to this sorry this okay, this picture didn't cannot show. Okay, so Kaya maybe yeah can get some new idea for high temperature superconductivity. Okay, it may be but I'm not so sure. May give us some new solution. Okay. Okay, so also we can do some study for the chiral transport. We can apply magnetic field and some edge phonons can transport can along this direction but cannot along this edge. Then we can manipulate this phonons. Okay, use some get to some this phonon be some phonon device. Okay, sometimes we can get some OR gate or some uh, switch effect for the phonons. Okay. Okay. So Californians nowadays becomes hot. Okay, now I just mentioned every year have more than 100 papers about this. So for nature science and maybe many papers cite this, and we also have California an international conference last year in Nanjing, and then 24 invited talks. And okay, so go to the conclusion. So yeah, in this talk, I talk about from the topological phonon to the phonon angular momentum to the chiral phonons and some new effect for chiral phonons. Okay, and in the future, maybe still need a lot of work to be done in different system and spin injection by common phonons and the superconductivities and the optomechanics modulation operation on a logic device for chiral phonons. Okay, and I will acknowledge from my collaborators and my teams. Okay, thank you for your attention. Thank you very much.
Yeah.